Assalamualaikum warahmatullahi wabarakatuh. I hope you still focus because since I'm the last person in the session, my name is Fathiya Rahmani. As a presenter under supervision from Fathiya PhD from Department of Physics, University of Indonesia. As we know that DNA acts as the genetic information carrier in our cell. But in bio-nanotechnology, we use DNA as a structural component. There are many attractive properties in DNA, such as self-assembly, self-recognition, and self-replication. And it makes the nanostructure shift of DNA can be controllable. Also, the DNA, the synthesis of DNA is less expensive than other molecules. And this is the DNA molecule that we all have known. And in figure 2, we see the DNA nanocube that has been fabricated by Shen and Siemens in 1991. And it shows us the flexibility of DNA that we can shape as we desire. And this is the figure 3. This is the DNA nanocube from the source from University of Illinois. And it can be used as a biosensor to find ion molecules in blood, tissues, and even this DNA nanotube can be used as the electronic circuit. In this research, we are focused on the charge transport properties in DNA that depends on first DNA model and sequence. And also, the charge transport properties in DNA also depend on environment influence, such as temperature, magnetic field, and electric field. From the previous studies, we know that DNA can act as a superconductor or even insulator. So, the question that we would like to answer by why we conduct this research is, how is the change of charge transport properties on poly-VG and poly-GC DNA molecule in electric field influence? So this is the theoretical model that we use that has been discussed earlier by my fellow researchers, Siemens and Rizky. So as I use the poly-VG and GC, so we just replace this into guanine and this into cytosine. And it is also the Hamiltonian binding that we use that also has been discussed by my fellow earlier. Besides transfer matrix methods, we also use scattering matrix that is used to observe conductivity in the molecule. So, we are going into the results and discussions. For this calculation, we use 4.2 K as the temperature and also crystal motion frequency as 0.21 megaelectronvolt. And we can see that from this transmission probability graph, the extended state band looks shift to the left, to the lower energy level. And it means that the electron is getting easier to move from left to right electron and makes the DNA more conductive. And also, even though we can't see it, it's visually insignificant, we can see that the extended band gap looks slightly widened. And it means that it offers new probability for electron to transmit at the lower energy. We also use the variations of voltage from 0 volt up to 2 volt that indicates if there are electric field influence. So after we get these results, we need to know what happens if we set the twisting motion frequencies higher. in the next graph, we see that we set the twisting motion frequencies into 1.02 mega electrovolts, and it looks it has a similar tendency. The extended band gets looks shift to the left, and the transmission probability also also increases as the twisting motion frequencies increase. And this is if we set the twisting motion frequencies very higher at 3 mega electron volts, and this is in 5.12 mega electron volts. And to make it clear, I make these comparisons of transmission probability on each frequency and voltage variation. We can see that as the twisting motion frequency is getting high, the transmission probability also getting high. And by the increasing of voltage, it looks you can see that the extended band shifts to the left, to the lower energy level. And the summary, the conclusions that we can take from my research is, as voltage increases, the extended state of energy band shifts to lower energy levels, and it makes the band and molecule more conductive. And the extended energy band widens, and it means that it opens new probability for electrons to transmit at lower energy. And as the higher twisting frequency is getting high, results in higher transmission probability and current. So this is the reference that we use in our research. And before I end my presentation, I would like to thank Daniel J. Hendro to give us the calculation, and also PKUI Research Grant that fund our research, and also UPPIPD, University of Indonesia, that give us the calculation facilitation. Thank you very much.
Thank you very much. Any question? Yes.
Okay, I want to ask about the research is modeling cycling method. Maybe is there any comparison or data experiment from it? And what is the usefulness after we calculate from the modeling cycling? Maybe you can explain me the usefulness of this calculation. For example, to give information maybe to biology researcher or application.
For the experimental results, I think some researchers have conducted that research experimentally, but I haven't seen it. And for the usefulness, we can see that by knowing the charge transport properties on this DNA molecule, we can know that the characteristics of charge transport. That's very useful in bio-nanotechnology field, especially to make the molecular device. Okay.
We still have another question.
May I develop the summary? Okay. I still don't understand about what is the twisting frequency. If the double helix is twisting clockwise or counterclockwise, what is the twisting frequency? I still don't know what is about twisting frequency.
Twisting frequency.
If the double helix is twist clockwise or counterclockwise or anything.
The twisting higher frequency is the parameter that we set. That it represents the twisting of the double helix DNA.
Twisting frequency higher. Okay. Twisting frequency higher is that the double helix is twisted again, or
whether the orientation of the twisting clockwise. Does it really matter whether it twists clockwise or counterclockwise? Or it's not completely irrelevant?
I think it's not
relevant.
it's not whether it's clockwise or counterwise, it doesn't matter.
Okay, I think we can have applause again for the speaker. Thank you very